Today's lesson is about integration by trigonometric transformation, applied to integrals involving product of powers of the sine and the cosine functions. At the end of this lesson, you must be able to evaluate integrals involving powers of sine or cosine functions or product of powers of the sine and the cosine functions. Okay, now let us look at the form of the integral of sine to the mx cosine to the nx dx, where at least one of the exponents, m or n, is a positive integer. It can be an odd or an even integer. Now let us take the case of at least one of these exponent is a positive odd integer. Looking at the case where n is the one that is a positive odd integer. Now the integral can be transformed into an equivalent form that we can easily evaluate either as power of sine x or power of cosine x. Okay, now the procedure to transform the integral is as follows. If it is n that is a positive odd integer, what we do is we split off a factor of cosine x, so that this particular factor of cosine to the nx is now expressed as product of cosine x and cosine to the n minus 1x, where n minus 1 is now a positive even integer. And as such, we can now replace that particular factor in terms of an expression involving the sine function, making use of this particular identity. Now, furthermore, we transform the resulting integral by using the substitution u is equal to sine x, and just work on an integral involving the variable u. Now, if in case it is the m exponent that is a positive odd integer, meaning it is the exponent of sine x that is a positive odd integer, then it is from this factor that we split off a linear factor of sine x, expressing it as product of sine to the m minus 1x times sine of x, where the exponent m minus 1 is now a positive even integer. And again, that factor can be expressed in terms of the cosine function using the same identity. And furthermore, we transform the resulting integral into an integral involving u, where u represent cosine of x. Okay, let us work with a particular example. To evaluate the integral of sine to the 7 2x cosine cubed 2x dx. This particular integral falls under the case of at least one of the exponents of the sine or the cosine function is a positive odd integer. In this case, both exponents are positive odd integers. So, to which factor do we apply the transformation? In a case like this, where both exponents are positive odd integers, we apply the transformation to the factor that has a smaller exponent. In this case, we will be transforming the factor cosine cubed 2x, okay, expressing this in terms of sine x. So it is from this factor of cosine cubed 2x that we split off a linear factor of cosine 2x, expressing that as product of cosine squared 2x with cosine of 2x. And to this factor of cosine squared 2x, which now has an even exponent, we apply the identity, where cosine squared 2x is equal to 1 minus sine squared of 2x. So replacing this factor with the said expression, the integral now is given in terms of the integral of sine to the 7 2x times 1 minus sine squared of 2x times cosine of 2x dx. At this point, what we do next is to multiply these factors, expressing this now as a difference of integrals given by the integral of sine to the 7 2x cosine of 2x2 dx minus the integral of sine to the 9th of 2x times cosine of 2x dx. Okay, at this point, if we will be applying the substitution, replacing sine of 2x by u with the differential du given by 2 cosine of 2x dx, or cosine of 2x dx is just equal to du over 2, then this given integral here can be expressed in terms of the new variable u as follows. We have u to the 7th. This is your sine to the 7th 2x. Then cosine of 2x dx is given by du divided by 2. So the first term is given by 1/2 the integral of u to the 7th du, and then the second term is given by negative 1/2 the integral of u to the 9th du. Okay, now applying the rule on how to integrate a power, then the integral of u to the 7th du will just be equal to u to the 8th divided by 8. Hence, the first term is now given by 1/2 times 1/8 of u to the 8th minus 1/2 times 1/10 of u to the 10th plus c. And if we will now be replacing u in terms of sine 2x, then this integral is given in terms of the variable x as follows. We have 1/16 of sine to the 8th 2x minus 1 over 20 times sine to the 10th 2x plus c. Let us take a look at the second example, where we need to evaluate the integral of sine to the 5th of 3x plus 1 dx. In this case, we simply have an integral involving a power of the sine function. But can we apply the transformation technique as explained earlier to this particular integral? Now, yes, we can. Okay, now since the exponent is again a positive odd integer, then we can apply the transformation by first expressing sine to the 5th of 3x plus 1 in terms of the product of sine to the 4th 3x plus 1 times sine of 3x plus 1. And to this factor of sine to the 4th 3x plus 1 with an even exponent, we apply the identity where we have sine squared of 3x plus 1 is equal to 1 minus cosine squared of 3x plus 1. Now, sine to the 4th of 3x plus 1 can be expressed as the square of sine squared of 3x plus 1. It is to this factor of sine squared of 3x plus 1 that we apply this identity that we have given earlier and express now the integral as the integral of the square of 1 minus cosine squared of 3x plus 1 times sine of 3x plus 1 dx. Now, expanding on the square of 1 minus cosine square of 3x plus 1, we will have 1 minus 2 cosine squared of 3x plus 1 plus cosine to the 4th of 3x plus 1. We multiply this with sine of 3x plus 1 dx, okay, and evaluate the integral. So for the product, we will have the integral of sine 3x plus 1 dx for the first term. Second term will be negative 2 cosine squared of 3x plus 1 times sine of 3x plus 1 dx. You have it there. And then the last term will just be in terms of cosine to the 4th of 3x plus 1 times sine of 3x plus 1 dx. Now, to simplify the form and the integral, we can make use of the substitution, replacing 3x plus 1 by u and 3 dx by du, or dx by du over 3. Hence, this given integral here can be written in terms of sine u, okay, dx is du over 3. So the first integral is 1/3 the integral of sine u du. The second integral is 2 times negative 1/3 integral of u squared du. Now, why a negative 1/3? If we will now have u to represent cosine of 3x plus 1, the differential du will be negative sine 3x plus 1 3 dx, or the product sine 3x plus 1 dx will just be equal to du divided by negative 3. That's why we have there a negative 1/3. And now, as to the last term, using the same substitution that we have here, then we will just have negative 1/3 integral of u to the 4th du. Now, evaluating the said integral, for the integral of sine u du, we will just have a cosine u, but u is 3x plus 1. Hence, we have 1/3 cosine of 3x plus 1. As to the second integral, the integral of u squared du, we apply the power rule, giving us the integral in terms of u cubed divided by 3. Okay, so this term will just be a positive 2/3 times u cubed over 3. And then the last term will be negative 1/3 u to the 5th over 5 plus c. But remember, your u here is cosine of 3x plus 1. Okay, so if we will now be replacing this u with the said expression, then the integral is just given by 1/3 cosine of 3x plus 1 plus 2/3 times cosine cube of 3x plus 1 over 3 minus 1/3 of cosine to the 5th 3x plus 1 over 5 plus c, or simply we have 1/3 cosine of 3x plus 1 plus 2 over 9 cosine cube of 3x plus 1 minus 1 over 15 cosine to the 5th of 3x plus 1 plus c. So in summary, an integral involving a product of powers of the sine and the cosine function of the form the integral of sine to the mu cosine to the nu du, where at least one of the exponents is a positive odd integer, can be transformed by applying appropriate trigonometric identities to an equivalent integral that can be evaluated either as a power of sine u or a power of cosine u.